All right, let's get started for today. Welcome to the 6th lecture of CS287, Advanced Robotics. One logistical thing, your homework 1 is due tomorrow, so keep that in mind. If you haven't started yet, start really soon. There's a late day budget and all that, but you might not want to use it on your first homework. Any logistical questions? Okay, then let's get started with lecture 6. There are actually a few things in, how can I swipe forward? A few things in lecture 5 that we didn't cover yet that I want to cover first. And actually a few pretty important things. So let's do a quick recap of the high level of what we covered in lecture 5. We looked at the linear quadratic regulator, which had some very specific assumptions, namely a dynamical system of a very specific form, xt plus 1 equals axt plus but, so linear system, and a very specific cost function, a very specific quadratic that's bowl-shaped with a clear minimum. And we saw that I'm going to try a few different settings here for a moment. Here we go. We saw that you can actually find a solution to this problem. Even though it's a continuous state space problem, infinitely many states, you can solve this by going through a set of iterations shown here. And so essentially have a bunch of matrix updates, and it gives you a feedback matrix and a cost-to-go function, a quadratic cost-to-go function. And the kind of surprising thing here was that the cost-to-go function stayed in the same format. You start with a quadratic, it continues to be a quadratic for all horizons. And so you could represent it exactly without any issues. Now, there were a lot of assumptions here in terms of what we assume. Linear system, quadratic cost. But then we saw that actually we can relax these assumptions quite a bit by using this as the building block to solve more complicated problems that are affine, have stochasticity, might be nonlinear. We might want to penalize for changing control inputs, could be time varying, and then could be trajectory following and even full optimization for nonlinear systems. And then we saw at the very end one example, cart pole. And I want to revisit that example now. So cart pole is a problem where you have 2 degrees of freedom, x-coordinate, and the angle of the pole, theta. And then the state space is 4-dimensional because there's x and the velocity, x dot, and theta and the angular velocity, theta dot. This is the equations describing how the dynamics of cart pole works. Clearly, this is nonlinear. But what we can do if we want to balance cart pole is we can say, OK, let's find the linear approximation around the equilibrium point, which is the one with the pole up and x at 0, and then run LQR on the linear proxy for the system, find the sequence of linear feedback controllers, or for infinite horizon, find the infinite horizon feedback controller, and use that to control the system. Now, if we start perfectly upright, nothing's going to happen in a simulator. But if we start from a state away from the equilibrium state, we'll be able to check if our feedback controller indeed brings us back to the equilibrium state or might fail. And you say, why would it fail? It's supposed to control us to 0, but that's only true for the linear system. For the nonlinear system, there's no such direct guarantee that it's going to go back to the equilibrium state. So we investigated that. And what we saw is that for this setting here, so we penalized for deviation from 0 for x dot, theta, and theta dot, but we don't penalize for controls. We have a reasonable subset of start states shown in green for which we get back onto the equilibrium state. The ones shown in red are combinations of start state specific x and theta combination for which running the linear controller does not succeed in bringing you back. Now, one question you could ask yourself is, well, since we approximate it with a linear system, and it's not that precise, is there any way, if we play with the cost function, that we might get a larger basin of attraction or a smaller basin of attraction, ideally larger though, because by playing with the cost function, we affect the trajectory that's being followed to the L0 state in the linear system that it thinks is going to be acting in. And if that trajectory keeps it in a part of the space where linearity is a good assumption, then that control will be applicable. But if that trajectory in the linear system space takes you in a part of the space where the linear approximation is bad, then the linear control might not work. And so by tweaking the cost function, you can affect where in the space you spend time and how good your linear approximation is. And actually, we saw at the very, very end, the last slide, last lecture, that here's a choice of cost function that doesn't seem that different. You now also penalize for controls. That's the only change right here. Used to be 0, now it's 1, and the basin of attraction has become a lot smaller. And at first, this is probably counterintuitive because you say, well, small controls means I'm in the linear regime, like a small control will still be captured well by the linear approximation. So you might say it's a good idea to keep controls small so I don't get the nonlinear effects. But actually what's happening here is that it doesn't care enough now about applying control. In the linear system, a little bit of control was enough to ultimately drive it back. And that was the minimum cost way to bring it back to 0. Whereas in the nonlinear system, if you're not willing to apply enough control, the pole will always start falling, and you need even more and more and more control once it starts falling, and you just can never bring it back up. And so often, it requires a bit of playing around with these cost function parameters to get it to work on a nonlinear system as well as possible. Any questions about this? Okay, then here's another idea. Imagine you have bounded controls. So your control input has to be between -1 and +1, let's say. Well, here's what you can do. You can change your dynamics. So original dynamics was xt + 1 equals f of xt comma ut. You do a change of variables. So you say ut is going to be tan h of vt, and this is the tan h function shown over here, which brings anything from -infinity to +infinity between -1 and +1. And by inserting that tan h there, your v can be any value from -infinity to +infinity again, but the dynamical system will only encounter the tan h of v, and so will only encounter things between -1 and +1. So then at control time, what will you do? Well, after you found your LQR-based controller, it would generate v. Because, I mean, LQR controls don't really pay attention to bounds on controls. So it would generate v if you set it up this way. And then you do a tan h operation on v, generating u, and you'd feed u into your actual nonlinear system that is being controlled by your policy. Now, often, it's still in addition helpful to penalize for v being too far away from 0. Why? Essentially, if your v ends up being somewhere here, or somewhere here, out there or out there, there's not much gradient signal to bring it back in. And so your optimization problem will not be very well conditioned. So what you might want is, you might some cost on v, quadratic cost on v, that looks maybe, I don't know, like this. Such that there's a natural force, everything else being equal, v will become smaller and will be brought into the part of the tan h space where you do get gradient signal. And then that means that you would very unlikely be spending time out here with v, because it's not really useful to be out there, because your effect on the dynamics is very minimal out there. And so you'd probably be at most, I mean, it all depends on details of the cost, at most be somewhere out here where you pay at least a smaller quadratic cost on v, and you also start seeing that gradient. And so you would get the gradient to bring you back to the other side if you need to, whereas if you are all the way out here and you don't have any penalty on v, and you're out here, you see no gradient, and you think you have no control over the system. And now the optimization problem will not find a good solution. Okay, so that's a way to deal with bounded controls, which is actually very often the case. Then now I want to do a little bit of theory, and we're going to do this relatively fast, because it's more kind of theory to kind of support the things we already know work, but to kind of give it even more justification than that, I want us to do a whole lot of theory here. Here is an important result. So you might ask yourself the question, if I design an LQR controller for a nonlinear system to stabilize around equilibrium, are there any guarantees at all that I can get for this controller? Maybe at least locally, get some guarantees. And it turns out, yes, there is a guarantee you can get locally. What is that? It's put on this slide here. Let's say we have an autonomous system. So the controls are ignored here. So imagine the feedback controls are already wrapped into your system. So your U has been replaced by K times X already, and now it's called an autonomous system. X star is an asymptotically stable equilibrium point for system F if there exists an epsilon bigger than 0 set for all initial states X, X minus X star smaller than epsilon. The consequence is that we go to X star. So it's saying if you start close enough to X star, the equilibrium state, you will be brought to the equilibrium state. If that's true, it's an asymptotically stable equilibrium. That's just a definition. And so the question we're going to ask essentially is along the lines of, if the linear system tells us it's asymptotically stable after we designed our controller, can we say the same thing about the nonlinear system that's actually under the hood? And the answer is yes. If we have an asymptotically stable equilibrium point for the linearized system, then it's asymptotically stable for the nonlinear system. Conversely, if X star is unstable for the linear system, it'll be unstable for the nonlinear system. And there's something called marginally stable, which is where you don't go to the equilibrium, you don't run away from it, you just kind of stay circling around it in a fixed orbit. Then nothing can be said, because then the linear approximation doesn't tell you enough about what will happen in a nonlinear regime. But this is a very strong result, because this shows us that once we design an LQR-based controller, at least very locally, it's guaranteed to work, and then hopefully it'll work wider than just super locally. Here's another idea that comes back a lot in control theory called controllability. What is controllability? So let's look at some definitions. A system is t time step controllable if from any start state x0 we can reach any target state. So any start state x0 reach any target state x star at time t. So that's intuitively something about how well you control the system, right? If you can go from any start state to any other state that somebody proposes to you, then clearly you have some control over that system. And t time step just means that you can do it in t time steps. Now, for the linear time invariant system, we can write out what the state will be at time t. It'll depend on the state x0, and then on the controls we applied from then onwards till time t. So we can now write out a condition for being t time step controllable. Our linear system A comma B is t time step controllable if and only if this above linear system here has a solution for all choices of x0 and xt. So we're going to fix xt, fix x0, because that's what we're asked to do, go from x0 to xt. And our freedom is in the u's. And the question is, can we find a sequence of u's that takes us from x0 to xt? If that's the case, if there's a solution for that for every choice of x0 and xt, then it's t time steps controllable. Now, remember your linear algebra class? A system of linear equations has a solution if it's full rank system of equations. So what does that mean here? If the rank of the matrix consisting of submatrices stacked next to each other is of rank n is the dimensionality of the state space X, then there will be a solution, or potentially multiple solutions, but at least one, and that's all we need. And then the system is t time steps controllable. Now there's a very interesting thing. We now know how to check if something is t time steps controllable. By the way, if it's not t time steps controllable, then if somebody asks you to bring something from x0 to xt in t time steps, you will just not be able to succeed for some combinations. Now, there's this other theorem from linear algebra that says that for all matrices A, for all t and n, there exists some weighting such that a to the power t is a weighted sum of, well, this should be really for all t. Yeah, that's fine. But we really care about t bigger than n is what we care about. that any higher power of A can be represented as a weighted sum of lower powers of A. So that's interesting, because what that means, if you look at this thing over here, we're looking at the rank condition. Once we go above n minus 1, a to the n minus 1, having a to the n times b, a to the n plus 1 times b, and so forth, what would happen kind of here if we continued is not able to increase the rank, because whatever we put in there is just a weighted combination of what we already had in the matrix. And if you just put something in that's a weighted combination of existing columns, you cannot increase the rank of the matrix. And so what this says is that if you want to know if your system is infinite time step controllable, you actually don't need to check this infinitely wide matrix to see if it's of rank n. It's enough to just check the one up to an minus 1b. That's enough to know whether anything beyond that will be rank n or not. If this is not rank n, nothing beyond it will be rank n. And so in control theory, people often study these conditions quite in a lot of detail and then say, okay, well, they'll make assumptions. They'll say, oh, we'll look at controllable systems. And that's actually a very reasonable thing to do. We've been looking at LQR without making that very explicit. But imagine you have an LQR system that you're trying to solve, and it's not controllable. Meaning, let's say you cannot drive it to 0. Well, then the solution we've been talking about, this notion that you could drive it to 0 and then have a steady state solution and so forth would not be true. It's only when your system is controllable, which we had as if there exists a path to get you to 0, then this thing will converge. This is a way to check this. We had that thing on early slides. If there exists a path to drive you to 0, we know this will converge. This is a way to check this. Check the rank of this matrix. If it's n, you're good to go. If it's not n, it might just not reach a steady state, and you might never be able to drive your system to 0. All right. Any questions about Lyapunov and controllability? Then let's look at another kind of pretty surprising thing, feedback linearization. So far what we looked at is linear systems, finding solutions for them, and then the system is nonlinear, we locally approximate it by a linear system. Feedback linearization is the idea that maybe you can find a global coordinate transformation that makes your original nonlinear system into a linear system. And if you can do that, that might be pretty handy, because now you can do a linear control and then do the inverse transformation when you apply your control on the real system. So imagine you have a system of this type. X dot is f of x plus g of x times u. X dot means time derivative of x. And this doesn't need to be scalar. This will typically be a vector x. Well, if g of x is square, means that requires number of control inputs is equal to the number of states. If that's the case, and g of x is invertible, then actually you can turn this into a new system by just a simple coordinate transformation. You introduce v as your controls, and now just have x dot equal v linear system. You solve your linear system, and once you solve the linear system, you know what v to apply in a given state, and then you do the transformation to u to know what control to actually apply to your real system. What's an example? Robotic manipulators. So robotic manipulators that are fully actuated tend to be governed by this equation over here. It turns out that you can essentially rewrite this as q dot double dot equal v. Q double dot is the acceleration vector for each of the joint angles in the robot. And then there's a nonlinear transformation you apply to go from v to torques, and then you can apply the actual torques on your robot arm. Note there are some tricky things here in that you might, at first sight, this looks really like almost perfect. You turn your nonlinear system into a linear system. But what you're kind of losing is that, let's say you now apply LQR, your quadratic cost will be in this new space. And maybe in this new space, the quadratic cost is not what you want. Maybe in the original space it would have made a lot of sense. Penalizing for squared torques might have made a lot of sense, might have made more sense than penalizing for, in this case, essentially acceleration. Maybe acceleration makes sense too, it depends. But after that coordinate transformation, your variables will be something different than what you started from. Now, you can ask the question, can we also do this when the number of control inputs is not the same as the number of states? Might that be possible? Let's do an example. So we have an example system here where we have one control input. One control input u, and two states x1 and x2. Let's see what we can do. Can we find a coordinate transformation such that this becomes a linear system? Well, here's what I'm going to propose. New coordinate z1 equals x1, so it stays the same. z2 equals ax2 plus sine of x1. Okay, that means in our new system, z1 dot equals x1 dot. Which we now need to fill out as minus 2x1 plus ax2 plus sine x1, which is actually equal to minus 2 z1 plus z2. So this equation comes out pretty well. z2 dot is equal to, we have minus x2 cosine x1 and then plus u cosine 2x1. Now we're going to need to use these equations to turn the appearances of x's into z's as much as possible. So let's see what we can do. We can actually write this as minus is that the correct one? Let's see. Minus 2z1 cosine z1 plus cosine z1 sine z1 plus, am I missing an a somewhere? Looks like I'm missing. Oh, here it is. Okay. Plus a u cosine 2z1. So this is by essentially writing x1 equal z1 and x2 equals, well, ax2 equals z2 minus sine z1. Okay, so now if we do a change of variables, where we call v equal to this entire thing here. So we'll call this thing equal to v. We end up with a linear system. z1 dot equals minus 2z1 plus z2, and z2 dot equal v. So that's pretty cool. It was possible. Yeah, go ahead.
Why did you get to plug in x2 prime for z2 prime?
Oh, you're right. I did something off there. I should have done, yeah, I did something off there. Should have been I should have taken z2 prime from here in the derivation. Yeah, so my z2 here, my z2 prime will have a ax2 prime. So I'll have, yeah, I should have done z2 prime equals ax2 prime plus cosine x1, and then start swapping in. So yeah, z2 prime equals ax2 prime plus cosine, I think it's cosine x1. Times x1 dot, something like that. And then from there, I get to the one below. Thanks. Now, when you look at this, it seems a bit magical, at least to me, that this happens to work out. And sometimes you can just do that. Sometimes you can look at your system and you can just turn it into a linear system by doing this kind of coordinate transformation. And here's the kind of the full version of this written out. But it's kind of surprising that this is possible, and you often are not going to know how to do it. But sometimes it's possible, and when it's possible, it's a nice feature to have, because now you can again rely on linear control to solve your problem and then do the inverse transformation when you run your system. It turns out that actually there's more to this. You can actually do some math, and I don't want to get into too much detail here, but if you look in the Slatina and Lee book, you can find a lot on that. That shows that essentially it shows conditions under which there exists such a transformation. So you can look at your system and write out some conditions which involve your f and g function. So here's some definition of what it means to be input state linearizable, meaning that if you're also allowed to do a transformation on your input variables, in addition to your state variables, can it be linearizable? And then there's some condition about some kind of field, vector field, being involutive and linearly independent, which is actually not that hard to check. If you carefully work through the definitions, you can actually check those things. It's reasonable to do. It's a little harder to actually find the solution that is the transformation. So to find the transformation that is the actual solution to this, you need to solve a partial differential equation over the space. And now, I mean, the whole reason we're trying to do, a change of variables is to make the control problem more tractable. If you can solve a PDE over the space, then you can actually just solve the Bellman equation over the same kind of grid that you would use for the PDE. And so there's little reason to do that. But sometimes that PDE might have a nice, clean analytical solution. And if that's the case, well, then you're in luck, and you can use the nice, clean analytical solution to the PDE to do a change of variables and have a linear system that you then get to control instead of a nonlinear system. I haven't seen people use this too much in practice, but it seems like something to be good to be aware of, because at least when you have a new problem and you have a nonlinear system, you could do a quick sanity check, like, are these vector fields of the right properties? If they are, then there exists a transformation. And then you could decide to try to solve that PDE and find that transformation, or you could decide that you can't do it, but at least you can consider it. So the slides here give a bunch more detail on the conditions to check. Not too important to step through all the details here, but keep in mind that this actually exists. There exist specific conditions, rank conditions on some vector fields of your f and g that show whether or not something is linearizable by a variable transformation. Okay, so here is a lot more to read on that. One thing you might wonder is, well, I mean, it's all great to, maybe there's a solution to PDE that can find this variable transformation, and maybe you can find it, maybe not, but actually maybe you can just learn it. So one thing you could consider as you're working on these problems is that, well, you could go from your original state space to a latent space, and you might just force the latent space to be a linear dynamical system. And if the latent space is linear dynamical and still models the original space pretty well that way by going to latent and then back, then that means you kind of implicitly, you found the transformation without explicitly solving the PDE. You found it by, let's say, training your system to be good at predicting the future, and directly that way found transformation that makes your control problem simpler. And so here are a couple of papers that do this. So the first one essentially puts the nonlinear system, in this case pixel space, so it's images where the dynamics is very much nonlinear, but it might be a card pole in pixel space or a linear system in pixel space. But in pixel space, it's not linear anymore, even if the underlying dynamical system is linear. And then you can, through a neural network, transform that into a latent space where you force the dynamics to be linear and you force the ability to predict the next state. And then you get a system that's easier to design controllers for. Deep spatial autoencoders does something similar, also for visual problems. And then Solar does it also, and it also looks at not necessarily vision-based problems. And Solar looks at the notion where it might be linear time varying rather than the same linear system at all time slices. And so that's, I would say, some kind of angle where learning and control have come together pretty nicely, where you essentially you learn onto something where we know that control can provide an efficient solution. And so you get the best of control, even though originally it wasn't applicable, but your learning is able to put it into the right mold. That was the last part for what we wanted to do for LQR and variance thereof. Any questions as we wrap that up? OK, then let's switch to unconstrained optimization. By the way, your homework 2 will come out on hopefully Thursday, maybe a couple days later, and will be on what we covered in the last 2 lectures. So LQR, iterative LQR, and extensions related to LQR. So let's reset for a moment. We try to solve optimal control problems in n-dimensional state spaces, and those problems are such that n tends to be higher than we can handle with discretization in many practical scenarios. So what are we going to do? Well, we need to do something else. What we saw so far is maybe if it's a linear quadratic system, we can actually solve it exactly still, or something close to it or approximatable by it, we can still do it. We can also kind of go back to the original question, like we're really trying to solve an optimization problem, find a sequence of states and controls that minimizes cost subject to dynamical system constraint, and maybe your controls and state have to be within some bounds. All right, so generally this is pretty hard to do because solving a general optimization problem is a hard thing to do. One thing we'll see something called convex problems, where this is actually very feasible to do. And again, we'll be able to use it as a building block to solve harder problems. So that's the main topic of the next stretch of this lecture. And then later we'll relax the assumptions to solve general problems. One quick note is that you can iteratively apply LQR. Is one way to solve this problem that I showed there, but the thing that's a little tricky to deal with is this thing over here, the bounds on the state variables. If you have bounds on state variables, you can have quadratic cost, things like that, but it's just a little tricky to deal with. Once we solve general optimization, we'll see another way to actually incorporate some of those ideas into LQR. We'll be able to do it with something called barrier methods that we can make part of LQR to keep state within certain bounds. But that'll take us a little while before we get to it. And what we've seen so far, this part is pretty hard to deal with. And what I show here, U is the actual controls. But in principle, U could be a parameter vector of a control policy. Maybe a linear feedback control policy, maybe a neural net feedback control policy. And you still have an optimization problem that looks like this. It'll just look slightly differently, where now you'd effectively have, instead of U, you could do it 2 ways. You could either say ut equals my policy pi theta of xt, or you could explicitly get rid of U and put just pi theta of xt inside there, getting rid of U. Either way, you can formulate this. So is the problem we're going to be concerned with. Once we solve it, we have a sequence of controls and states. We can apply the sequence of controls, and hopefully that works. In practice, if there is noise, if there is unmodeled dynamics, if there is, mostly noise and unmodeled dynamics, what will happen is you will deviate from your trajectory, and your sequence of controls might not be appropriate anymore. So you'd have to re-optimize to find a new sequence of controls from that new starting point and repeat. That's receding horizon planning if you do it over a certain horizon that you're able to look forward. And then again, actually, once we start doing that, we might again want what we covered in LQR, which is we might want a quadratic cost-to-go function at the end or some cost-to-go function at the end to be able to cap it off such that we're only looking 10 steps ahead computationally, which maybe is all we can do, but then we have a cost-to-go function after that that effectively allows us to look until the end of time. All right, recall that we actually have seen a method for solving problems like this, a black box method. Cross-entropy method, and you're actually implementing this in your homework 1. So this is a very simple method. It's maybe not the most efficient in general in terms of running time, but it is typically the most efficient in terms of the amount of time you spend coding. And so usually you want to implement this first because it'll take you almost no time and it'll give you at least a baseline of what you can expect from an optimization. If you don't do better than this, probably your optimization is not set up very well. So quick reminder, what's cross-entropy? You optimize some function f of x. So we try to find some x. But actually, instead of finding an x, we're going to try to find a mean of a Gaussian distribution that is centered in a good spot in the landscape of f of x. We'll start with some initial mean, a guess of the mean. Could be 0, could be whatever. We don't really know. If we don't know anything about f of x, we don't know what it should be. We pick just something. Then we iterate outer loop. Within each iteration, we sample x from our current Gaussian with current mean and some variance, let's say. We compute f of that x. And we'll compute a bunch of these pairs. And then once we've gotten a bunch of those pairs, we look at the average of the x's that were in the top 10%. And that's where we're going to reposition the mean of our Gaussian, and we repeat. Very simple process. All you need to be able to do is just sample from a Gaussian, evaluate your function a few times, rank them, find the top 10%, average the location of those, and repeat. It actually works surprisingly well. So highly recommended to always try whenever you're doing any kind of optimization. Now, what this does not do is that it turns out with modern packages for the cost of an evaluation of a function of f, if you're willing to pay twice that cost, you can get derivatives of that function. And derivatives point us in the direction that the function will be lower and where we need to go. And so instead of kind of just dropping dots into the space and hoping some of them land good and then going closer there, if we actually also take advantage of derivatives, often we can do better. But now also keep in mind, some functions don't have derivatives everywhere. And so if your function is not continuously differentiable, then a derivative-based method might have some issues, whereas cross-entropy method will just not care about that. It's totally fine with functions that are 0 everywhere and then 1 in some region and then -1 somewhere else. It's all fine. And very key thing, though, is very easy to implement. And so you usually want to do this first. All right, now let's take a look at problems we can solve efficiently with existing tools. The ones that can be solved efficiently are called convex optimization problems, and at the core of it, there are convex functions. What's a convex function? Convex function is one, and the function here is shown in black. So f of x shown in black. It's a function where if you take any 2 points, so x1 and x2, see what's the function value, you draw the line between those 2 points, that line lies above the function. If that's the case, we have a convex function. The way it's shown here is for a 1D function. But actually, this is the same for any dimensionality you have. Let's say you have a 2D function. You can still take 2 points, see what the function value is, connect a line between those function values, and then see if that's above the function or not. And actually, you'll be checking along a line, and you'll be seeing something that just looks like a planar slice of that function. Same for higher dimensions. You take any pair of points, you look at the line along those points, and see if it's above the function or not. So visually in 2D, it might look something like this. what's also interesting about it is that if you have a convex function, the contours are all convex shapes. So convex function is where the line is above the function. If you interpolate between 2 points, a convex shape is one where if you have 2 points that are part of the shape, then if you connect those 2 points, the line between them is also inside that shape. And so you see here the contours are all convex, and this is guaranteed to be true for a convex function f of x. What that also means is that if you look at the set of points f of x smaller than some fixed number a, for example 0 or some other number a, that set of points will also be convex. And so a convex optimization problem is one where we minimize a convex function f0 subject to some other convex functions fi of x smaller than 0, and you can have a linear constraint. Let's think about this for a moment here. We have a set of convex functions, and for all of them we require fi of x smaller than 0. So each one of those generates a convex region that you need to be in, and we're effectively intersecting those convex regions and saying that's where you need to be. But again, the intersection of convex regions is a convex region, so overall we end up with a convex region that we're optimizing over. And this thing here is just kind of limiting it to, it doesn't have to be one constraint, it could be multiple constraints, so essentially limiting us to some linear subspace where we are only allowed to find solutions. Everything outside of that hyperplane or outside of a line or whatever it is, depending on how many equations there are there, is not allowed. What's on it is OK. That's also convex, because when you have a plane, connect any 2 points on the plane, you're still inside that plane. OK, so the interesting property is that problems of this type are solvable very efficiently. So if ever you run into a problem that is of this type, you know you can find an efficient solution. In fact, there are existing packages out there that you can just call upon that will solve these problems for you. Now, what we're going to do is we're going to split how we look at these problems into 2 parts. There is this part, and then there's this other part. There's the optimization objective, and there's the constraints. Today, we're going to look at unconstrained problems. So we're going to, for now, ignore constraints. That'll be for Thursday. We're going to look at problems that only have an objective. And on Thursday, we'll see that the building blocks we get from looking at problems that only have an objective are quite reusable with a little bit of extra machinery to also deal with ones that have constraints. So then it's called unconstrained minimization. First thing we're going to look at is, well, let's first center ourselves on what we're actually doing. This is all we're doing. Minimize over x, f of x. And actually, the way we're going to look at it is we're not going to necessarily require f of x to be convex. We can think of it as convex. We know that then there's efficient solutions. If non-convex, the things we'll see will actually be finding local solutions, but not necessarily globally optimal solutions, but they'll still work. Well, what can you do? The natural thing to say is, well, I have an optimization problem. I want to find an optimum. Set the gradient equal to 0. Set all derivatives equal to 0. It means that no matter which coordinate you change, the function is not changing. So I'm at some kind of local maximum or minimum. I don't know maximum or minimum from just the first derivatives. So I need to look at second derivatives to see if indeed I have a minimum. If that's the case, then I'm good. And this here is the second derivative, the Hessian matrix. If that's positive definite, meaning locally the quadratic is ball-shaped, then we have an actual minimum. OK. In simple cases, you can actually solve this directly. And that's very convenient. You can just say, OK, I have a system of equations under 2. It'll be as many equations as unknowns by design. That's just how it is. Derivative with respect to every coordinate equal to 0. So there's an equation induced by every coordinate. So as many unknowns as equations. See if you can find a solution. But often that equation will be nonlinear in some way that is very hard to find a solution. And so you won't be able to do it. Then, if you do find a solution, you check if the second derivatives are all positive, which means you're in a minimum, and then you're done. Now, in practice, we're going to have to resort to other things most of the time. We're going to have to resort to a more iterative procedure, where when we have some function f of x, let's say x1 squared plus x1 x2, bless you, plus 3x2 squared, then we're going to have contours, and we're going to try to find our way to the bottom. It's like essentially just you have a landscape, and it's a ball rolling down a hill, or a person skiing to the bottom of the mountain. finding the little bottom spot there. Question now, of course, is how do we actually make this happen? And this will be the core of what we're going to be doing for the current next and next lecture. So let's make sure to kind of gradually spell it out. Okay. So the core of it is going to be steepest descent. What is steepest descent? It's a very simple few line algorithm. So steepest descent says init x, repeat, determine steepest descent direction, which we'll call delta x. Then it might be that if we just walk in that direction, like the slide here, if you just walk in that direction too far, you're actually going uphill again. So don't want that. So then you do a line search. Which means choosing a step size t bigger than 0, because you want to go in the direction of steepest descent. And then we update x becomes equal to x plus t times delta x. And we do this until some stopping criterion is satisfied. Okay. So then a natural question is going to be, which direction is going to descend the steepest? How do we find that? And then we'll also need to figure out how we do the line search. There's two big components here. Actually, let's take a couple minutes break here, and after the break, let's look at those two components and how we can resolve those.
Yeah, no, I caught up on sleep. I think I'm probably going to take just have too much. So I like 3 or 4 things to do.
All right, let's restart. Any questions about what we have here? Okay, then let's see how we can find the steepest descent direction. Well, it's a local thing. We're at a current point. And so let's say f of x0, our current point, plus some change, delta x, is going to be approximately equal to first order Taylor expansion, f of x0 plus gradient with respect to x at x0 transpose the change delta x. Now the question is, what's the steepest direction of descent? Then what we want to do is, steepest means that, let's say we only get to move 1 meter, and we can choose the direction in which we're moving in our landscape. When are we going to be the lowest? Which direction gives us the most vertical descent if we only get to move 1 meter, so in a small radius? So making this more explicit, let's say we're looking for the minimum over delta x such that our norm of delta x, let's say, is smaller than some epsilon, so we can only stay close, of f of x0 plus delta x f x0 transpose times delta x. Now this thing here has no delta x in it, so the minimization is not affected by this term, so we can just get rid of it. So we're really trying to find the delta x that minimizes this thing while your delta x has to be small. Well, this is just a vector, that's just a vector. We know that if we try to find, for any two vectors a and b, minimum over b, such that norm of b smaller than epsilon of a transpose b, then we need to take b equals, in the direction of a, but actually the negative direction of a. So we need to take b equal minus a over the norm of a times epsilon. This is saying I'm going to take a vector in the exact opposite direction of a, because I want to minimize this quantity. And minimizing means that I want to have a negative sign here in that resulting thing. And so I have an a pointing here. I get to choose b anywhere on this small circle. I want to pick b in the opposite direction of a all the way till the end of the circle that I'm allowed to move in. So b is going to be here, and this is the equation for that b. Same thing here. This is going to be, then our delta x is going to be negative gradient of f at x0. Then we need to normalize it. And times epsilon to be staying within this circle. The a here is really the gradient of f at x0. And our delta x will be this thing over here. So that's the steepest descent direction. Now, we know we're just really looking for a direction. So, I mean, the epsilon doesn't really matter. We're just looking for a direction. And the renormalization doesn't really matter either. These are just rescaling. What we really care about is that it's this direction we should go in, and how far we're going to go is anyway going to be determined by the step size t. So if all we care about is steepest direction of descent, we can make it as simple as delta x equals negative gradient with respect to x f at x0. So we now know this thing over here. Steepest descent direction, delta x, negative gradient with respect to x, f of x. So that's resolved. Now, we need to find the gradient. That's just a bunch of derivatives. Either we can use an automatic differentiation package, or we can do finite differences. We just do plus epsilon minus epsilon for each coordinate, take the difference, divide by 2 epsilon, we know the gradient. OK. Now, the next thing we have to do is find t. Something called exact line search. Says min over t bigger than 0. Oh, well, the slide is s, so let's call it s here. Min over s bigger than 0 of f of x plus s. So let's just call it t. T delta x. So we just need to find the best t. It's like we walk downhill, and whenever things start going back up again, we went too far, we got to stop. That's what that is doing. But how are you going to find this? Exact line search is hard to do, because you might not have an analytical form of the function along the line you're walking in. If you do, then that's great. You can just take it and you're done. But typically, you won't have an analytical form along that direction. And then you have to, in principle, try infinitely often until you find a t that achieves the lowest. You might be able to do some kind of bisection search, find like the one, like narrow it down to a small interval. In practice, people do something a little different most of the time, because this is not possible to do exactly. Do something called backtracking line search. So let's take a look at that. So backtracking line search. I'll first write out the algorithm, and then I'll make a drawing that will give us more intuition about why what we're writing up here is meaningful. So we set t equal to 1. And then we say while f of x plus t times delta x. Remember, our delta x is negative gradient of f of x. While f of x plus t delta x bigger than f of x plus alpha, which is a hyperparameter t gradient f of x transpose delta x. While this is true, t becomes beta times t. And here, alpha is in 0, 0.5, and beta is in 0,1. So let's take a look at what at a high level is happening. What's happening is that we try some step size, and if the condition is met, in this case means we're unhappy, because we're going to keep going in this loop. If the condition is met, we're unhappy, we're going to shrink t, make a smaller step, and repeat. Why might this make sense? We're doing a steepest descent thing. We know that at least locally, we should be descending. Right? And so if we take a very small step, we should have a descent, and it's good. So there's going to be this kind of loop where we're always making our step size smaller, 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 till finally we're happy with it. And we start ideally somewhat large, such that if we're lucky and we can take a big step, and this condition is not met, that means we exit the loop, then we're done. OK, so now this condition here governs whether we're happy or unhappy with our current step size. So let's take a look at a drawing to understand what this is really looking at. Let me draw it over here. We have our t-axis, our t0 that we started with, let's say, or our current guess, we have our t equals 0. We cannot go below 0, because then we're stepping in the opposite direction. We're going to go up instead of down. So we know we've got to be somewhere there. We also don't want to make it tiny from the beginning, because then we don't make much progress. So we're always going to start with something relatively large and then backtrack to make it smaller until we indeed are descending. Now, the simplest thing you might have thought, like as a first thing you might have come up with, instead of the condition here, you might have said, instead of this thing here, you might have said, while, you might have just said, oh, what if I just do this and ignore the later part, right? That would be fairly intuitive. You say, while when I make my step, I'm higher than before, it's bad, I should shrink my step size and repeat. That's very logical. But then there's an additional thing here that's saying, actually, it's a stronger condition. It's saying, I need to also, this is in some sense some margin. It's kind of saying, I don't want to just be better than I was before. I should be better by some kind of margin in some way. And that's what we're going to look at what this extra term is doing. But this should be very intuitive, that if you are bigger than where you were before and you're trying to descend, clearly your step size should shrink. There's just a little extra thing coming in here that we want to pay attention to. So here's your function. Now, let's take a look at this thing here. What is this? As a function of t. Let's ignore alpha for a moment. Let's say alpha equals to 1. Then what this is essentially, it's saying, I'm looking at my linear approximation of my function f of x. That's all it is. It's saying how far, essentially saying, I could put the t here, like delta x times t. This is how far I'm stepping, right? And this is the gradient. And so I'm just looking at the linear approximation, but the rescaled version of it. So the linear approximation might go like this. And in that rescaled version, alpha is between 0 and 0.5. So what that means, it's essentially pulling the slope of this thing closer to 0. It's changing the slope, bringing it closer to 0. So with an alpha that's not 1, it'll look something like this. And now what we're saying with this condition over here is we're saying that we want it to be the case. We're comparing f. So let's pick some value and see if we exit or not. I'm going to pick something far out first, so we might have a higher chance of having to backtrack. So let's say we pick this one over here. That's our t. We're going to look at f of x plus t times delta x. That's the point over there. And we're going to compare that with the kind of less steep approximation, this one here, and see which one is higher between the two. Clearly the function f of x is higher over there. So this condition is satisfied and we're unhappy. So we're saying f of x is higher than what this thing said it should be, so we're unhappy. So we're going to backtrack, scale t down by some factor beta. Maybe now, I don't know. Maybe now we end up over here. We're going to do a new comparison, and again, f of x is above this linear thing that we're comparing with, and so we got to further shrink. And the crossover point is going to happen here, which on the slide is called t0. But since we rescale by beta, there's no reason we'd land exactly on that t0. Maybe on the next one we land over here, and now we compare and we say, okay, we're happy, condition is satisfied. So I mechanically stepped you through it, what's happening. Now let's interpret this. What this is saying essentially is that we have a linear approximation that predicts some improvement. But because the function is bowl-shaped, the linear approximation will always be optimistic. So expecting to improve as much as the linear approximation is too much to hope for. But maybe we can scale down a little bit. The alpha is scaling down a little bit what we can expect based on linear approximation, and now it should be achievable. And so that's what the alpha is doing. Say, okay, linear, f is never going to go down as much as the linear approximation because it's a ball-shaped function. But if we scale it down a little bit, then f should be dipping below it. And we should be able to take a step size that gets us in the region where we're actually below that less optimistic version of how steep we can go downhill. And so that's what it's doing. Another way to think of it is that if your function f of x falls above this dashed line, it means your linear approximation was a bad approximation. Because that dashed line gives you some prediction of how much descent you can expect. And if you don't get that, it means you had a bad approximation. Can't trust the linear approximation. You're probably going in the wrong direction. You should probably be going in a different direction at that point. Step size is too big. Whereas if the function is below the dashed line, it means you're probably still in the regime where your linear approximation is pretty good, and you're happy to take the step and then repeat. This is called backtracking line search. Sometimes has other names like Armijo, stepping rule. It turns out that aside from being fairly intuitive, it also has nice guarantees. So when people try to come up with guarantees, can I solve in a, let's say, finite time, get within some epsilon of the optimal solution of my problem? Well, you can't do exact line search because exact line search will always take infinitely long for one line search. So you need to rely on something approximate. And this is the kind of approximate line search where you can guarantee that in a finite number of steps, you'll find something, and then you'll have a certain level of improvement and repeat, and that'll allow you to prove convergence guarantees of algorithms that use this in finite time as opposed to an inner loop that takes infinite time to do exact line search. Any questions about this? Yes?
Why is alpha between 0 and 0.5? Why isn't it like 0.8?
It's a good question. I don't remember for sure. I suspect there are some guarantees that depend on it if you build on top of this, but I'm not 100% sure. Beta is usually chosen pretty close to 1, like 0.8 or 0.9 in practice, such that you, whenever possible, take relatively large steps. But yeah, why alpha cannot be, it might be just heuristic or it might be for guarantees. The closer you pick alpha to 0, kind of the bigger your steps are going to be that you allow, because closer alpha to 0, the shallower the dashed line will be, and so the further out you get to go, but also kind of the riskier, because the less you can trust your approximation. Yeah, it'd be worth looking up at some point.
I have a quick question.
Sure, there's a couple of questions. Let's see. Eric, is this on? Go ahead. Why don't you go first?
All right, sure. So if you have a really complicated loss surface, it seems like it would be possible to jump from one, let's say, convex region to another convex region. In practice, have you seen that to be an issue?
Yeah, that can happen. And then, I mean, it's not even clear why you want it to be in the one versus the other in the first place, so it's not clear whether you care or not. Most of the algorithms are more focused on the notion of locally guaranteed to find an optimum, and then if that local optimum is not the one you want, then maybe you reinitialize and find another one. So yeah, it can happen, but I don't think people are particularly concerned about it. In fact, sometimes they might even encourage it by having multiple initializations and finding multiple spots, or adding noise. Something people will do is sometimes add noise to the gradient a little bit, just in case there's like a really tiny optimum that you don't care about. It's like this tiny little thing, but there's actually just this tiny little dip. It's like you're going over a mogul when skiing down, and there's like a little dip there, and you don't want to be stuck at the bottom of the mogul. You want to keep going. Essentially, if you had a little bit of noise, you wouldn't be stuck in that little dip. So people play little tricks like that. But there's another question in the back, I think. Oh, okay.
Is the initialization to t equals 1 arbitrary? Would you start from t equals 100?
Initialization to t equal 1 is arbitrary. Yeah, it's just to pick something. And honestly, it's very arbitrary, because if you think about it, look at gradients. If you rescale your function, right? If you rescale your function f of x, like maybe you have a new function, g of x, which is 100 times f of x. Okay, but you don't know ahead of time which function you're working with, of course. But let's say you have you have one algorithm. You're going to run it both on F and on G. And you run it on F, and on G, at first you might say, oh, well, I want the same behavior. I want it to, do the same thing. But then how's that going to happen? If you look at the gradient, the gradient of G at X will be 100 times the gradient of F at X. So your starting attempt with t equal 1 will be 100 times bigger, even though the landscape of the function is the same. It's just like everything's been scaled up. But if you look at the contour lines, nothing has really changed by rescaling. And so, yeah, these first order algorithms have arbitrary scaling in them. And so you just kind of need to be somehow lucky with where you start. And maybe you have a hyperparameter where you decide where you start. Or you might do something where after you've done this shrinkage, right, and you ended up with a step size you like, you took a step. Then for the next one, you might start with not exactly that one, because that would be very conservative, but maybe you start with that one scaled up by a little bit, like maybe scaled up by 1 over beta, or scaled up by 1 over beta squared, to go a little bit back up just to see if it might work there. And that way you'd need to do less of those inner loop evaluations. A lot of it will also depend on how expensive or cheap it is to do this line search. Sometimes that's super cheap, and then you care less and you can just do it. Otherwise, you want to really optimize for getting that first one already pretty precise, and then you might want to keep some memory around about what you did in the previous iteration. But for the very first iteration, when you start it all off, it's not clear what you're going to do, just because of this reason here. Like, somebody can just rescale your problem, and when you thought t equal 1 is perfect, well, if they rescale by 100, you actually now need t equal 1 over 100 to have the same thing. Yes?
Why not just try different, fixed step sizes instead of adaptive step size?
Well, the question is, why not try fixed step sizes? This is something you can get nice guarantees for, that in finite time you're going to improve on your optimization problem, on what you score in your function in a consistent way. If you just try a bunch of different step sizes, see what happens. Yeah, I mean, in principle, you could have a bunch of step sizes. I mean, you could parallelize this. You could try t, beta times t, beta squared t, all of them in parallel if you care about wall clock time rather than compute cycles. And then you could, try a bunch of them at the same time, see which one kind of lands in the best spot, and go from there. That's definitely a possibility. Yeah. So, So we found the steepest descent direction is the direction of the negative gradient. Exact line search, maybe sometimes feasible, usually not. So we looked instead at backtracking line search, something that has nice guarantees and is relatively simple to implement. There's the picture motivating it that we also draw on the board. And then this is the full algorithm, gradient descent with backtracking or exact line search, depending on what you want to do. The stopping criterion we didn't talk about. Stopping criterion is when the gradient is smaller than some eta. It's typical to do. Again, it's a funny thing, because if I scale up my function by a factor 100, then my stopping criterion will be 100 times harder to satisfy. But it's not clear what else to use in this kind of first order setting. Here's an example of this in action. On the left, we have backtracking line search. On the right, exact line search. On the same set of contours, same function, f of x1 and x2. And we see that it kind of goes downhill. And in the backtracking line search, well, it's an aggressive step, but it satisfies that criterion. It goes a little further than the exact line search, but ultimately gets there pretty efficiently. This is a low-dimensional problem. You could say, well, how much do I lose by using this backtracking line search compared to exact in a higher dimensional problem? So x is 100-dimensional here, which means AIs are all 100-dimensional vectors. And it's this is the problem. And if you look at the horizontal axis number of iterations, vertical axis is how far from the optimum measured in log scale. And what we see here is something called linear convergence. If the vertical axis is measured in log scale, horizontal axis is just normally measured linearly. If you see a line, that's called linear convergence. And that's what we have happening. And actually, backtracking line search, exact line search is fairly comparable. Not a very big difference here. Now, here's another example. Quadratic, a parameterized quadratic, where we have x1 squared plus gamma times x2 squared. So it looks something like this, gamma bigger than 0. And then if you do exact line search, what you can do is you can actually find, for this case, you can find the exact solution. You can actually write out the sequence of x's you will find. And this is a sequence of x1s and x2s that you'll find running exact line search on this objective. Now, if you look at this, you'll see that, I mean, it needs to go to 0. If gamma is very large, so gamma is bigger than 0 here, if gamma is very large, then this ratio will be roughly 1. This ratio will be roughly -1. And so what you'll get is that you have 1 to some power, -1 to some power. It just kind of doesn't really go anywhere anytime soon. It's very slow convergence. Whereas if gamma is close to 1, what happens is, if it's actually 1, then it's easy. Gamma minus 1 is 0. Gamma minus 1 is 0. It lands onto 0 right away. If you look at it more closely for different values, the closer to 0, the faster this, the closer to 1, the faster this will converge. The further away from 1, the slower this will converge. Pictorially, equal to 1 means the contours will be concentric circles. When you're moving away from 1, then it'll become ellipses that are very horizontal or very vertical, depending on whether you go towards plus infinity or towards 0. And when you get those elongated contours, things converge a lot more slowly. Why? Because the gradient will kind of go, it'll kind of hop back and forth this way. And the more elongated, the more it'll just hop up and down rather than going down to the middle. So that's a bit of a challenge that happens with gradient descent. So something called condition number, which is the ratio of the highest second derivative to the lowest second derivative in absolute value. But in this case, if we're convex, they're all positive. So condition number says how poorly are you conditioned. And the reason we just need to look at the highest and the lowest is because if we just look along those two dimensions, that's where the worst case behavior will happen. Everything else will behave better because it's better conditioned relative to each other, but those two are going to be the worst, and they're going to control how slow it is that gradient descent will converge for you. Since only the two extremes matter in high dimensional spaces, it's almost guaranteed, unless you're very careful about designing your problem, almost guaranteed that they'll be far apart, that ratio will be a high number, and so that you'll have a poorly conditioned problem and slow convergence of gradient descent. Just kind of too bad, but that's just the way it is. So what we're going to look at next time is some fixes to that. So on Thursday, we'll cover a bunch of fixes that will recondition our problem to be better behaved. See you in 2 days.